Today we're going to be discussing magnetic fields of a bar magnet. The purpose of this lab was to determine the magnetic dipole moment of a bar magnet by collecting experimental data using a smartphone magnetometer, analyzing that data using logarithmic regression, and then comparing the results to a computational model we created in GlowScript. The main physics fundamentals for this lab include understanding magnetic fields, magnetic dipoles, and the equations that describe how these fields behave. And here are the results for our lab. The main results are as shown. On the bottom is the table from the first part of the experiment, which we put into Excel, and then we have the graph that it created. And below the graph is the results from the second part of the experiment, which we'll talk about later. Here are the other results. We have the slope of the graph that was negative 1.04, the scale factor, and the magnetic dipole moment, which was 2.07. I also concluded that the magnetic field was near zero far away from the magnet, and then it increased as it got closer to the magnet. In this experiment, we used a magnetometer app to measure the magnetic fields at strengths various distances from the bar magnet along three directions: parallel, perpendicular, and at a 45-degree angle to the magnet's axis. The system consisted of the magnetic field in the space where it existed, and then we have the surroundings, which included the external magnetic sources and the environment noise. Our initial conditions involved zeroing out the background magnetic field and keeping the magnetic orientation consistent as we recorded our data. We then put that data into Excel, which you saw from the results earlier. Here's the math which we used to find the results from earlier. First, we have what we got from Excel, and then we have where we found K using a logarithmic regression, and then we have the magnetic field equation, and then we solved for U, which is our magnetic dipole moment, and then we found U. And here are important equations that we use for the GlowScript, which helps us replicate our experiment. The formulas here are the magnetic field of a dipole, magnetic field on axis, and the equation for a magnetic field at perpendicular points. And these were all key for our code. First, we have a function that calculates the magnetic field vector B produced by magnetic dipole with a magnetic moment mu at position vector r. It uses the dipole magnetic field formula, which depends on the distance and direction from the magnetic observation point. And then we have the perpendicular field calculations. The code calculates the magnetic field at four positions, perpendicular to the magnetic axis: up, down, forward, and backwards. For each position, it calculates the vector from the magnetic field to that point, and then uses the function that we created to find the field. And then it visualizes an arrow, which you'll see in the model later on. And at the final part of our code, we calculated the 45-degree off-axis using the formula from earlier. And here are the results that we got. The computational model results show that magnetic field values along the magnetic axis and perpendicular to it, with on-axis fields around 6.8 times 10 to negative 3 teslas, and the perpendicular field is negative 3.435 times 10 to negative 3 teslas. At the 45-degree off-axis position, the model predicts a magnetic field of approximately 1.11 times 3 to negative teslas, when compared to the actual experimental measurements with 6.4 times 10 to the negative 5th at the same position. This difference is significantly large. This discrepancy could be due to idealization in the model, measurement errors, or difference in the experimental setup, but the model has effectively demonstrated the expected fields of the relative field strengths. But this also could be due to human error in the math or in the experiment if I did something wrong. And here's the model that we produced in the code. As you can see, we have our bar magnet in the middle and the fields around it. Now, what if? What if we hadn't aligned the meter stick to cancel out Earth's magnetic field? Well, the readings would likely have been skewed or inconsistent due to the interference from the Earth's horizontal field component, making it harder to isolate the magnetic contributions. Now, what if we used two identical magnets that were stuck end to end? Well, the total magnetic moment would double, which would increase the magnitude to the field everywhere by a factor of 2. Since the magnetic field strength from a dipole is directly proportional to the dipole moment, this would make the computed and possible even experimental values noticeably stronger. Now, we performed this experiment to explore and visualize the magnetic field of a bar magnet using both experimental measurements and computational modeling. The goal was to better understand how magnetic fields behave in space and how the dipole moment predicts these fields. And we concluded that the U was 2.07, and then and there was no we did have slight errors due to human error in the code, or in the experiment and then the math. Thank you.